Can we really drink ocean water? The shocking truth revealed. So oceans dominate our planet, stretching across an astonishing 70% of the Earth's surface and accounting for nearly 97% of all the water on Earth. Standing on a beach or gazing out across the vast blue horizon, it's easy to imagine the ocean as an almost infinite reservoir, capable of solving any water shortage humanity might face. However, the reality is far more complex. The critical barrier that keeps us from simply tapping into this boundless supply is salt, which permeates every liter of seawater with about 35 grams of dissolved salts, a mixture that's undrinkable and dangerous for humans.
Drinking seawater directly is not merely unpleasant. It's hazardous. Our bodies are finely tuned to handle only small amounts of salt, and the concentration found in ocean water overwhelms the kidneys. Desperate ingestion of seawater actually dehydrates us faster, stresses our organs, and ultimately leads to serious complications, including kidney failure and death. That's why, throughout history and into modern times, humans have relied on comparatively scarce sources of fresh water: rivers, lakes, rain, and underground aquifers. Transforming seawater into something safe to drink is possible, but it requires removing the dissolved salts and minerals in a process called desalination. This is no simple task. Desalination at scale is an intricate, resource-intensive, and expensive endeavor. Even with the most modern technologies available, there are two principal methods currently used around the world. The first is thermal distillation, which essentially replicates the sun's ancient process of evaporating water, leaving the salts behind, and then condensing the vapor into clean, drinkable liquid. The second, and now more common, is reverse osmosis. In this sophisticated process, seawater is forced through highly specialized membranes that are engineered to block salt and other impurities, while letting only pure water pass through. Reverse osmosis is more energy efficient than traditional distillation, yet it still requires tremendous energy and complex maintenance, making it largely unattainable for many regions, especially those with limited infrastructure or financial resources. Desalination's formidable challenges go beyond cost and complexity. The process generates vast quantities of concentrated brine, water even saltier than what went in, which typically gets dumped back into the ocean near the plant. This spike in local salinity can disturb delicate marine ecosystems, harming organisms that can't quickly adapt to such changes. Moreover, the power needed to drive these plants commonly comes from fossil fuels, linking desalination directly to carbon emissions and the broader problem of climate change. Despite these barriers, researchers worldwide are racing to find better answers. Innovations like forward osmosis, solar-powered desalination, and membranes made from cutting-edge materials, such as graphene, promise breakthroughs. These emerging techniques offer hope for cheaper, more energy-efficient desalination. Yet most are still experimental, or only work at limited scales, far from serving mass populations. Another issue is geography. Many of the world's largest and thirstiest cities aren't right on the coast. Transporting desalinated water vast distances inland adds layers of logistical and financial strain. For most communities, even in water-stressed areas, it's currently much more feasible to rely on local freshwater sources, though these too are under growing pressure from pollution, overuse, and climate-fueled droughts. As the technology evolves, experts warn against seeing desalination as a cure-all. If viewed as an easy fix, it might sap the urgency needed to protect rivers, wetlands, and other vital natural sources of freshwater, paving the way for environmental decline elsewhere. Operating desalination plants also demands a skilled workforce and a steady stream of expensive replacement parts, costs that can be out of reach for many developing nations. While the dream of turning ocean water into a daily source of drinking water for humanity remains powerful, the path to making that vision real is one paved with scientific, environmental, and economic hurdles that we're only beginning to solve.